Welcome to MEERTALK. My name is Kathy Posey, and I'm the Director of Administration at MEER. We're really glad to be getting together for another MEERTALK. Today, we will be hearing from Jessica Wan, and then we'll take questions from people in the MEER community. And after that, we'll open it up for some questions from all of you in our audience. Dr. Tao is currently in China to establish new academic collaborations and explore potential research partnerships. In order to carry out the research critical for MEER's further development, we do rely on donations. If you don't already donate and you'd like to contribute toward our efforts to cool the planet, we appreciate your donations. You can go to meer.org/donate, and we thank you so much for your contributions. You can also write to info@meer.org to be in touch. Now, let me tell you about our guest speaker. Jessica Wan is a climate sciences PhD candidate in Dr. Kate Ricke's lab at Scripps Institution of Oceanography at the University of California, San Diego, studying how climate geoengineering proposals, particularly marine cloud brightening, might alleviate regional climate change impacts. She's also a National Defense Science and Engineering Graduate Fellow and an Achievement Rewards for College Scientist Scholar. Prior to coming to Scripps, she graduated from Cornell University with a Bachelor of Science in Environment and Sustainability with distinction in research. If anyone has any questions that come up while Jessica is presenting, please send them to co-host Barbara in the chat. Okay, Jessica, we're eager to hear what you have to say, so please take it away.
All right. Well, thank you for having me today. I'm really excited to share with you all some, basic overview on marine cloud brightening, as well as some results from a recent study that came out. So the title of this talk is Marine Cloud Brightening in a Changing Climate. And like I said, I'm just going to go through some introduction on marine cloud brightening, and then delve into some results from the paper. This is really a spotlight on this recent publication called The Diminished Efficacy of Regional Marine Cloud Brightening in a Warmer World, which you can check out via this QR code, and I'll spotlight it up later at the end of the talk too, if you want to find more details after the talk. And this is in collaboration with some folks at the National Center for Atmospheric Research, Jack Chen, Simona Tilms, Yagar Victor, as well as some colleagues at Scripps, Matt Luongo, and my advisor, Kate Ricke. All right. So as most of you in this room are probably aware, progress in responding to global warming is really quite slow and honestly insufficient to staying well below 2 degrees Celsius. And I kind of like to use this graph here to motivate this type of work. It's from the United Nations Emissions Gap Report that came out a couple years ago now. And it really shows, how far we have to go if we follow current emission trajectories through 2030 and how far we need to reduce those emissions in order to meet the temperature limits set by the Paris Climate Agreement. And that's a lot of gigatons of CO2. And so there's a huge gap between where we need to be and where we're currently headed. And that climate crisis has really motivated a lot of this type of research on alternative mitigation strategies called solar geoengineering. And for those of you who aren't familiar, solar geoengineering refers to any sort of activity that moderates warming by either increasing the amount of sunlight reflected back to space or by reducing the trapping of outgoing thermal radiation. And there are sort of three main types of technologies that people have deemed as maybe the most promising so far with research to date. Probably the most well-researched one is stratospheric aerosol injection, which operates kind of in the highest part of the atmosphere here in this diagram by increasing the scattering of particles in the stratosphere. Kind of in the mid-level is cirrus cloud thinning, which operates by reducing that trapping of outgoing thermal long-wave radiation. Probably the least well-researched of these three, but still kind of out there right now as a probable way of doing this. And the last one is the focus of this talk, which you all came to listen to about. It's marine cloud brightening, or MCB, which operates in the lowest part of the atmosphere here by increasing the scattering of low marine clouds. So that's kind of the big overview of solar geoengineering. But I'm going to go into a little bit about how we think this technology might work through a little schematic. So you could imagine that there are a bunch of ships out there in the world that have these specialized nozzles attached to them that can spray sea salt into the lower atmosphere. And that's kind of how we think this could happen on a larger scale. And so if you have all these boats deployed, they're spraying sea salt into the lower atmosphere through a series of microphysical and macrophysical processes. They're able to kick off all of these changes into the clouds to activate into cloud condensation nuclei. When you have more droplets for a constant amount of liquid water in these clouds, you get a lot of small droplets, and they are more reflective. So that's kind of the primary way that rain cloud brightening would work. When you have a lot of really small particles as well, you inhibit precipitation formation because it takes a lot more of these little particles to hit each other to form large enough droplets to rain out. So that leads to clouds that last longer and that are more reflective, which lead to cooler temperatures. And that's sort of the big goal, the objective of marine cloud brightening. Can we produce cooler temperatures through this pathway of processes? And if you want to learn more about kind of just the physical science of how marine cloud brightening will work, I'm just going to plug this review paper that came out recently that kind of walks through the state of the knowledge on the physical science for marine cloud brightening research and kind of where we need to go if you want to learn more. Okay, so this is kind of how marine cloud brightening is hypothesized to work. And a lot of studies to date have focused on these large-scale implementations of marine cloud brightening. So cooling, huge percentages, half of the global ocean, something like that. These really large international efforts. But on the flip side, there's been a lot of research that's been rising recently on regionally focused interventions. And kind of the big one that happened back in March of 2020 was the Australian government-funded marine cloud brightening project to brighten clouds over the Great Barrier Reef as a way to, cool locally just over the reef to save the reef from rising ocean temperatures. And this was kind of the first, real effort of marine cloud brightening, or at least testing the technology for marine cloud brightening out in the real world. That kind of inspired me to get involved in this research at the beginning of my PhD. Since then, actually, just this year, there was another experiment off the coast of Alameda, California, run by the Marine Cloud Brightening Project, the University of Washington, where they were also testing equipment, specialized nozzles to increase the reflectivity of these clouds, see if they could perturb the clouds in a significant way. So there's kind of a few of these experiments out there for marine cloud brightening in the real world, for more regionally focused endeavors. Outside of marine cloud brightening, there's been some work in China for weather modification for a while. And if we look at, things outside of even real world, there's been a lot of modeling studies in the scientific literature on other types of regional geoengineering, such as this paper that came out a few years ago now on artificial upwelling in the Indian Ocean to try and reverse droughts in the Sahel. So there's kind of a whole variety of regionally focused interventions that are now in the literature and in the real world that are kind of motivating this type of work. So the question we are trying to answer in this project is whether or not regionally focused marine cloud brightening in the North Pacific can mitigate extreme heat in the Western United States. And this is sort of an interesting question for two reasons. The first is that the Western United States is already experiencing some record-breaking heat waves due to global warming. And, I'm originally from the Pacific Northwest. There was a really big heat wave that hit a few summers ago back in 2021 that was really detrimental. It was lethal. It killed a lot of people in both the Pacific Northwest and Canada, as well as was harmful to the local ecology and, the fisheries industry out there. On top of it being a region that's susceptible to heat waves, this is an interesting question because the northeast subtropical Pacific has been identified by the existing literature as somewhere that might be susceptible to cloud brightening. And the region I'm talking about here is the subtropical stratocumulus cloud deck off the coast of California, where we see this persistent, really large deck of low clouds that are there for most of the year. So you see this elevated low cloud fraction here in this green polygon. Not only do we see this in the satellite images, but this has been a region that's kind of been deemed as one of the 3 main stratocumulus cloud decks in the world. That would be a good candidate region for marine cloud brightening. It's been included in most of the early modeling studies on this topic. And it's also been identified as a region with susceptible meteorological conditions by the aerosol cloud interaction community, so both by the modeling and the observational community. So this is kind of the classical region where people have thought we could do marine cloud brightening, the subtropical stratocumulus cloud deck. I'm also going to propose a competing hypothesis of doing mid-latitude marine cloud brightening kind of near the Aleutian Islands as a way to elicit a remote response to the Western US. And the motivation for this is really this nice study by Yue Dong back in 2022, where the authors imposed this artificial cooling in the South Pacific mid-latitude region. And by doing this, they were able to kick off a huge chain of feedbacks that really started by just cooling locally in this mid-latitude region, but were able to advect across the whole Pacific basin, strengthen the subtropical high, speed up trade winds, and kick off dynamical feedbacks. And if that means nothing to you, then really what you need to take away from this study is that by cooling this one region, they're able to enhance, spread, and sustain that cooling pattern throughout the entire basin. And when we look at the modeled low cloud cover in the model that we're using for this study, we see there are a lot of low clouds up here in the mid-latitude region. And so, when we see this elevated low cloud fraction here, that implies maybe that would be a good spot for marine cloud brightening. And if it is, could we elicit a similar response, but in the other hemisphere? Okay, so how do we do this? We are using a model called the Community Earth System Model version 2, CESM2, in order to conduct these simulations. This process starts with identifying the grid boxes with the highest low cloud cover in order to brighten. So we want to brighten existing clouds in our study. So we want to find the regions with the most clouds. And once we do that, we're able to develop what we call these MCB seeding masks, which are implemented in our climate model as a constant increase in the cloud droplet number concentration to 500 particles per centimeter cubed, up to a total of 2% of the global ocean area. And we create these masks for 9 months out of the year, March through November, and turn off marine cloud brightening in the winter months, December, January, February, in order to kind of simulate what would, you probably not want to run this in the winter when there's less incoming solar radiation. And we develop these masks for both the mid-latitude region up here, as well as a subtropical region, kind of that classical region. And finally, we run these through a fully coupled cyclical CSM2 simulation, both with and without marine cloud brightening for our 2 different regions for 2 different time periods. So I'm going to call the present day simulations, which are 2010 cyclical emissions, as in average conditions from a 2010-like world, and a mid-century warming scenario where we have 2050 emissions, or SSP 245 mean emissions around 2050. And those are sort of our 2 main periods for each of these marine cloud brightening strategies. And that's what I'm going to be showing in the results from here on out. Okay. So the first big result of this study is that under 2010 conditions, we find that both the subtropical and mid-latitude marine cloud brightening strategies are able to produce global mean cooling. And so I'm showing here on the left, panels A and B, those are the same low cloud cover maps from before, both the observed and the model CSM2 cloud cover. And then in panels C and D on the right, I'm showing you the temperature response due to the marine cloud brightening in the mid-latitudes in the top and marine cloud brightening in the subtropical patch on the bottom. And you can see that you get pretty strong cooling throughout a lot of the Pacific and this northern hemisphere snapshot here under both of these strategies, with potentially more cooling in the mid-latitude case. But if you have a keen eye, you maybe noticed here in this bottom panel that the model seems to have a lot more low clouds in the mid-latitudes than perhaps there are in the real world in the satellite record. And so you might be wondering, what is the effect of this low cloud bias in the model? And so if we normalize the global cooling by the global forcing, so we account for that bias in the low cloud cover in the model, we find that actually the global cooling response under the mid-latitude marine cloud brightening is smaller now. So that's that number in the top right corner of these panels. But the cooling in our target region, which is outlined in that black polygon, is actually still larger under the mid-latitude marine cloud brightening. So that suggests that, you know, even though there is this low cloud bias, and when you normalize it by that forcing bias, you're still able to get a larger cooling response in the target region under mid-latitude marine cloud brightening. Okay, but both are cooling. That's the takeaway under the present day conditions. You might be wondering why it's so effective, brightening clouds in this mid-latitude region, and we propose this kind of dynamical pathway here in the paper as to why it might be effective. Essentially, it leans on that study that I showed by Yue Dong, where when you brighten clouds up here in the mid-latitudes, the mean wind state in this region advex southward along the coast, and you get this pile up of sea level pressure along the coast of California, which then speeds up the wind along the equatorial Pacific, and you get a bounce back of all these Rossby waves that's able to sustain the cooling. And that's kind of this feedback, positive feedback that makes the cooling stronger and sustains it in this region. Okay, so that's kind of the bigger picture, but our target region was the Western US. So what's happening there? We find that both of our interventions are able to reduce the dangerous summer heat risk under these present day simulations. And that's what's shown here. If you look in panel A, I'm showing you the relative risk of heat reduction for different heat thresholds. There's the danger one up top, which is the most severe, defined by the National Weather Service, down to extreme caution and caution. And you see that the mid-latitude present day simulation in this orange circle has the largest relative risk reduction, whereas the kind of solid triangle here for the subtropical marine cloud brightening also has a pretty large relative risk reduction, and the largest compared to the other heat thresholds. And these maps here on the right are just showing the distribution of where those changes are happening, with the total exposure for danger in panel B, and then the relative change for each of the MCD strategies in the pink and green here. So it looks like our interventions are actually pretty effective at reducing dangerous summer heat risk under present day. But when you then fast forward to look at the 2050 results, we find that not only are you ineffective for the same marine cloud brightening strategies at reducing the relative risk of heat exposure, but you're actually counterproductive for some of these heat thresholds, where you're actually increasing the amount of heat exposure that you would have had without any marine cloud brightening at all. And so that's kind of concerning, because we are currently in, present day light conditions and not ready to deploy marine cloud brightening. This is something that might be considered in the future. And if you change the base climate state, these same interventions become less effective. And that's what we're seeing here. And not only is this the case for our target region in the Western United States, but we're also seeing that marine cloud brightening triggers unintended side effects in remote regions as well. And this includes probably the biggest finding, which is hotter summers in Europe under this 2050 mid-latitude marine cloud brightening strategy. And that's what you're seeing here in panel C, this warming effect here. You also get warming over North America and parts of Asia. Not only do you see these, remote side effects in temperature, there's also remote side effects in precipitation, with potential drying, along the coast here, as well as areas throughout Africa and the Sahel. And we attribute this result to a state-dependent response in the Atlantic meridional overturning circulation, both to greenhouse gas warming and marine cloud brightening. So essentially, AMOC is expected to weaken under mid-century warming conditions, both in this climate model and in across the CMIP6 models. And when you have this weakened AMOC state in the future, when you apply, so you have a weakened AMOC state in the future. That's what's shown here. All of the simulations have a lower AMOC strength. When you apply marine cloud brightening in the future, you're able to spin up AMOC a lot more under this weakened state than we were in the present day state. And that's what we're attributing this change in the response to this weakened AMOC state. Okay. So just some quick takeaways from this. I think one of the biggest ones is that targeted marine cloud brightening can mitigate extreme heat stress, and we're finding that both of these strategies, both the subtropical and mid-latitude strategies, are able to reduce that regional extreme heat through this change in the upstream dynamics and the resultant teleconnection. We also find that marine cloud brightening may become ineffective under global warming, and we attribute this state-dependent response to a change in AMOC strength under mid-century warming, making the intervention effective under present day, but potentially not under mid-century warming conditions. And finally, we find that the effects of regional marine cloud brightening can be pretty unintuitive. And this really illustrates the challenges that we may face as scientists and decision makers if climate risk management remains largely ungoverned as it is today. Finally, I'd just like to acknowledge the funders of this work, particularly the NSF and CAR Early Career Faculty Innovator Program that really made this work possible. And yeah, I guess I'm a little bit early, but hopefully that's okay. Leaves more time for questions. I'm happy to take any questions now, and thank you for listening.
Thank you so much, Jessica. Next, we are going to bring on someone from MEER who would like to ask you some questions. And just a reminder that our audience can send questions to Barbara, co-host in the chat. So we have with us today Robert Tulip. Robert Tulip has worked in geoengineering advocacy since 2008 on both carbon dioxide removal and sunlight reflection methods. He worked in international development for the Australian government for 30 years and has a Master of Arts honors degree in philosophy for his thesis in existential ethics. He lives in Australia and is on the steering council of the Healthy Planet Action Coalition. He worked closely with Stephen Salter, marine cloud brightening pioneer, for 2 years before his recent death, and has a good understanding of the technology and politics of marine cloud brightening. And it's about 4:30 a.m. in Australia, so extra special thanks for joining us, Robert.
Thanks so much. And Jessica, what a fantastic presentation. I think that your work is of immense value, and I read your paper as well as your talk, and so really appreciate seeing what you're doing, and what you're showing is that if marine cloud brightening is just done in one spot rather than globally, then the results of it might be different from what people expected. It might have a warming impact. I'd like to go first to this question around the Atlantic meridional overturning circulation, and as most of us may know, the AMOC is slowing down, and the result of the slowing AMOC is major climate disruption. So it's perceived as one of the biggest climate risks in terms of a tipping point, and the effect of the slowing of the Gulf Stream in particular, the northward flow of water through the Atlantic, is that the warm water that currently brings to Western Europe would stop, and there would be a really big cooling for Europe, and that would be a catastrophe for European agriculture and climate in general. So one of the perverse effects of global warming could be a regional cooling in Europe, and what your analysis seems to suggest. You talk about spinning up the AMOC, and I'd just like to clarify, by spinning up, do you mean that the AMOC would speed up or wouldn't slow down as fast? And
Yeah.
And so the issue is that well, we really want to retain the AMOC, and you're saying that MCB would mean that AMOC, regional MCB in the North Pacific, would have this teleconnection, that is a connection between one region of the Earth and a completely different region in the Atlantic, that would mean that by doing MCB in the North Pacific, it would protect the AMOC, and that would have an overall planetary warming effect. So I wanted to check that understanding is correct first, and just see if that raises issues for you.
Yeah, no, that's a great question. Thank you for bringing that up. So based off those plots that I showed, kind of with those dots and how they changed under the 2 time periods, in that AMOC slide, you can see that the 2050 dots don't quite bounce back up to where they were under the 2010 levels. So we're not restoring AMOC's strength back to present day levels with marine cloud brightening. We're just reducing the slowing, if that makes sense. So that's what I mean by spinning AMOC back up again. We're able to basically cause this artificial cooling in the North Pacific, which is creating a lot of this dense, cool water up there in the mid-latitudes that's able to then sink and kind of kick the system back up again. So when you cause this temperature imbalance between the 2 basins at that latitude, we're causing cooling in the Pacific. That means somewhere else in that same latitude band has to warm as well. And because we're cooling the Pacific, that means it's happening in the Atlantic. So that's kind of what we're finding, or one hypothesis for why we see the responses that we see in this study.
And so what that illustrates is that really to do MCB effectively, it does need to be worked out on a global basis. That is, if you only worked in the Pacific and didn't do anything in the Atlantic or the Indian Ocean, then you would have these unusual effects. But if you did do a coordinated global MCB effort, then you could really optimize the results. And so it's this global optimization and the need for a governance system. So something like an international albedo union that would just go through all of the MCB proposals and optimize them for the, like, people complain about there's a risk to the monsoon, there's a risk to Africa. Like if you tried to cool down Europe, then you might heat up Africa or change the rain. But these need to be understood against the risk of doing nothing, which is absolutely immense. Like, we face really quite catastrophic risks if we don't do anything to reflect more sunlight. So we have to work out how to reflect more sunlight, and we need the international governance rather than just proceeding on a regional basis. How do you see those issues, Jessica?
Yeah, that's another great point. I think, in an ideal world, we do have an international governance structure in place that can manage kind of a global coordinated effort of something like marine cloud brightening. I think where this work is coming from is a place where that's going to be really challenging to achieve international coordination about this type of topic. What if a country or an actor somewhere in the world wanted to go out and do this? For example, the Western US was like, it's really hot here. Let's go out and do marine cloud brightening. What would the effects be? And as it turns out, the study shows it wouldn't be very great. So it needs to be a coordinated effort. And that's sort of what this work is substantiating, kind of a need for both regional, local, and country level, as well as an international governance structure for this type of science.
So finally, this raises the question of the role of the Intergovernmental Panel on Climate Change, which has basically completely rejected marine cloud brightening as an option. That's my perspective on it. Like, so for example, the summary for policymakers in the latest IPCC report did not mention planetary albedo, reflection of sunlight back to space. It just left it out because it's so controversial. And so what I would like to see is a complete reversal of the IPCC priorities. What they should recognize, in my view, is that that emission reduction is just incredibly difficult. And, they've got the plan to say, let's get everyone to cut emissions in half by 2030. So that's what the IPCC says. But actually, emissions are accelerating. They're not reducing at all. So it shows that the political appetite for emission reduction is just really low. And so we're on a really catastrophic path, because if we put all of our eggs in the emission reduction basket and say, oh, we're not going to do any MCB or any other sunlight reflection, then the risks are just so bad. So what I would like to see the IPCC do is reverse its priorities and say that sunlight reflection ought to be the most urgent thing. So we can reduce extreme weather in this decade, and hopefully biodiversity loss and sea level rise and some of the risk of tipping points. If we go full speed on marine cloud brightening, getting governance, getting the technology sorted, the technology, there's been so little money in this that people don't even know the technology issues, then, we see like this lack of support means that when the University of Washington did that test in Alameda that you mentioned, the immediate reaction from the local council was to shut it down. And so that's been a bit of a disaster, because it just shows that there's a lack of public debate and understanding about the moral value of going ahead with both with the research aiming for deployment. So I'd really welcome your thoughts on those issues, Jessica.
Yeah, I mean, you bring up a lot of really good points there. I think, the conversation around solar geoengineering, marine cloud brightening has really changed in the past, even since I started my PhD, I think, the past 4 years. I think, at least in the US, that we're seeing, the government, the federal government, start to even mention climate intervention, geoengineering in their research priorities. That report came out, I think, in the past year, where they even mention it. It used to be so taboo that they couldn't even mention it. I think a lot of federal science agencies like NOAA are also starting to invest in research in geoengineering, climate intervention work as well. And so I think there is kind of a momentum towards putting more resources into this type of research, but maybe not at the pace that we need to see in order to start actually developing the technology and the international government's structures for this type of science. So I think there have been steps moving in that direction, but maybe not quite at the level that we need it yet. And yeah, I think you're totally spot on with your points about the IPCC really needing to start talking about this topic rather than just leaving it out with their reports.
I'll make one final issue, and that is the reliability of the models. And so one of the issues is, as you pointed out, the real world is so complicated. It's hard to be certain that the models are right. And so there's going to be a big role of learning by doing, that people will really need to do field tests and see what actually happens from the field tests to see if the models are right. So I'm just wondering what how reliable do you think the modeling work that you've done is?
Yeah, I mean, this is really results from one climate model. So firstly, we need more, multi-model comparisons of these types of interventions because climate models are pretty unreliable, especially when you just have results from one. So we need to be doing this with different modeling centers across the world, having their models repeat these sorts of experiments to get some robustness on the results that we're seeing from these large-scale interventions. And then we need to also, that's kind of like the biggest scale and the most theoretical. It's a climate model. I think we need to also develop at smaller scale models, like large eddy simulation models. Do we actually see the changes that, I walk through in that chain of causal interactions that happen when you inject sea salt into the air? Do we actually see those same processes happen where cloud droplets get smaller and brighter and all of those processes work in the large eddy simulation? So those are smaller models of clouds. And then, yeah, we need to do more field tests to see if this happens in the real world. So I think we have to develop the science from, field testing, real experimental work through our smaller process level models all the way through these large global climate models in order to get the full range of certainty across these scales. Yeah, and that's a big challenge.
Fantastic, Jessica. Thanks so much. That's all from me.
Thank you very much, Robert, for your questions and comments. We would now like to open it up so that we can hear from you, our audience. So we invite you to continue to write your questions into the chat to Barbara. And so we do have a question from Jonathan. Jonathan asks, please would you explain the information in slide 12 showing that the net cooling effects were not due to reflection of sunlight from the mid-latitude clouds, but from a change in equatorial water or equatorial cool water flow. If you need me to repeat that, let me know, Jessica.
Yeah, no, I have slide 12 pulled up. Thanks for your question. So yeah, this is sort of a mechanism that we developed to explain why the cooling that happens in that mid-latitude region from rain cloud brightening under over the Aleutian Islands, how that then translates to this basin-wide cooling throughout the Pacific. And so the pathway that we kind of hypothesized here is that when you cool local temperatures and sea surface temperatures up in the mid-latitudes, just the basic wind flow in this region is to move from this mid-latitude region down the coast of the Pacific Northwest all the way down through California before it then loops back to create the trade winds. And so if you rely on those natural climatological winds, you're able to advect those or blow those cool temperatures southward. And then when you have this movement of really cold temperatures moving southward, you get essentially a strengthening of the subtropical high pressure system that's off the coast of California. And when you get that really high pressure buildup, it essentially is like creating a lot of really heavy things in one area, and then they all topple over. And that's what happens when you then move to speed up the trade winds that move westward across the equatorial Pacific. And then when you get a speed up of the trade winds, those happen naturally, but now they're faster than usual. You're able to kick off a bunch of equatorial processes like Rossby waves through dynamics in the climate system. And when you get this tapping into Rossby waves and these faster trade winds, you're basically creating this positive feedback of cooling and faster trade winds that then enhance the cooling again. And that's how you're able to get the sustained and enhanced cooling throughout the Pacific. Hope that answered your question.
Thank you, Jessica. We have, so we do have a request, Jessica. If you could leave the information, the DOI or other link for the research that you mentioned so that we can follow it up.
Yeah, where would be a good place to put that? Can I reshare the screen
or
yeah,
in the chat, or either way, or reshare the screen? Well, probably in the chat because we've got you spotlighted.
Perfect.
Okay,
yeah.
Thank you. Okay, and we have a question from Mark. How many years do you think it will be before a fairly clear understanding of the complexities of MBC will be known? In other words, when can it be said that MBC is likely to work or not likely to work to cool the planet?
I think if I had the answer to that question, I would have solved the real issue here of climate intervention. That's a really good question. I think it's hard for me to say as a PhD student in this field when we'll know for sure whether we're certain. I don't think we'll ever really know for certain whether we're ready to start deploying this type of technology. But I think I can say for certain that we're not ready right now. There's so many, like I've mentioned, from this physical science perspective, there's so many uncertainties still because marine cloud brightening operates at this huge range of scales from really tiny microphysical cloud processes all the way to these large scale global teleconnections. And we have to have more certainty at each of those steps before we'll even feel good about the physical science of doing this. But then, we've also talked about with Robert earlier, like the governance structures are not there either. And so until we have, the physical science, the social science, the governance more in place, we're not going to be in a place where we feel good about doing this type of technology in the real world. But we want to have, as much research and knowledge as possible before we have to make those decisions, before climate change becomes bad enough that we have to start, reaching to the bag of these more alternative solutions. But definitely the priority has to be emissions reductions, and this stuff is going to come in as kind of like a add-on to that.
Thank you.
Yeah.
Eric has a question. Ignoring the future effect of climate change on the efficacy of targeted marine cloud brightening, the study seems to find that present-day intervention is effective. How does the energy needed to deploy MBC techniques at scale compared to the cooling gained?
That's a really good question. So I think what you're getting at here is, how many ships would you need to go out there, and what would be sort of the emissions from ships constantly spraying sea salt for 9 out of 12 months. And I wish I had an answer for you, but honestly, the economics and feasibility side of this work is also pretty lacking at this point. And part of the reason is we don't actually have the technology developed. The sprayer technology is kind of in prototype land with the folks at UW and the folks in Australia. And nobody's able to do this at a scale large enough to have a detectable change in the climate system yet. So we don't really know actually how many of these sprayers you would need, if the sprayers are even the best way to do this type of climate intervention, and how many boats you would then need, and what types of emissions, would they be running in clean energy, that kind of stuff. So it's hard to say what the exact cost comparison would be there between the brightening that we would see and how much it would actually take to go and do this. Yeah.
Thank you. We have a question from Herb. Can you adequately field test MBC to determine global impacts without actual massive global MCB deployment?
That's another really good question. It's slightly outside the realm of my expertise with climate modeling. Yeah, I'm not really sure I can give you a good answer. I think the challenge of doing field tests is that when you're out in the real world, testing these sprayers, it's hard to know what the counterfactual is. So like, what would have happened to these clouds if you had done no brightening at all? That's something that you can easily test when you're in a model. You have a simulation with it and without, and you can do the difference, which is what we show here in this study. But in the real world, you don't have that, counterfactual. You don't have that world in which you didn't perturb the cloud because you've just tested it. And so I think that's going to be really hard to get a certain answer at a scale that would be, able to have some sort of certainty. So that's outside of my realm of expertise, how people do that in observational experimental world. But I don't know. I don't have a good answer. Sorry.
No, thank you. Jonathan asks that Dr. Salter postulated that the mist from the devices sprayed in the open ocean would not simply fall onto the sea surface because of the physics of aerosols. How much of the outgoing mist would actually form and brighten marine clouds?
That's another good question. And again, I'm not a good expert in this particular topic of marine cloud brightening. In the models, we kind of, we assume that we're actually able to inject some sort of aerosol into the clouds, and we're not even doing that. So we've assumed that you were able to inject some sort of aerosol, and then actually what we do to simulate the climate effect of marine cloud brightening is just increase the number of droplets in these clouds. So we're assuming that the aerosols have worked as anticipated. I think obviously if we were going to go do this in the real world, you would need to have certainty from the sprayers emitting stuff, how much of it actually ends up in the clouds. And that's what the folks at, UW and Australia are trying to figure out now. I think, the physics behind why people think this is a viable mechanism, spraying mist into low marine clouds, is because you get a lot of updraft naturally. That's how you form these marine clouds in the first place. So you're kind of relying on the existing meteorological conditions in order to get that mist updrafted into these low clouds and not just fall right out into the ocean. So I can't give you a number. I'm not really sure if anyone actually could give you a number right now because we're still developing these. The royal we, not me, but people are still developing these nozzles right now.
Great. Thank you. We have a question from Mark. How do you explain the lack of research on simpler SRM strategies, such as that being studied by MEER? Is it a lack of interest, of funding? Is it partly due to the need for academics to avoid trying to publish on subjects not already being widely written and read? What are your thoughts?
Yeah, so I guess we're talking about, like more infrastructure type things, changes on land, albedo changes. And that's a really good question. I'm not actually sure why the community has focused so much on these, larger scale dynamic changes like marine cloud brightening, like stratospheric aerosol injection. I think potentially part of the reason might be, these other technologies like stratospheric aerosol injection and marine cloud brightening have these natural analogs in the real world. For stratospheric aerosol injection, that would be like volcanic eruptions. That's kind of the basis for why people even thought about stratospheric aerosol injection in the first place. We have seen effects from volcanic eruptions. With marine cloud brightening, the natural analog is ship tracks. So we see these brightened ship tracks when ships emit sulfate or into the clouds. And so these technologies have a physical basis for why scientists think they might work. I think with these land albedo modifications, potentially there's not really a natural analog like we have for some of these other types of intervention strategies. And so maybe scientists haven't grabbed onto them as much because it's harder to show that, we have a natural mechanism for how this would work. But that's a really good question. I'm not really sure why.
Thank you. Thanks for the question. Jonathan has a comment. During your talk, you mentioned that cooling on one ocean area at a certain latitude needs to be balanced by heating in another ocean at that latitude when discussing the Pacific and the AMOC area. Is this must be balanced a general rule?
Basically, it's just leaning on kind of an energetics theory that, the world likes to smooth out temperature gradients. That's why we have these large scale ocean circulations. The Earth system is always trying to move warm air, warm ocean temperatures that are generated in the equator towards the poles. And likewise, the poles are cooler. So we try and smooth out those temperature gradients. When you cause a temperature gradient kind of in the zonal direction or east-west direction, similarly, we have to balance that. The world doesn't like to have a really cold patch in one spot and a really hot patch in another. So that's why it's kind of spinning up this global ocean circulation again to try and balance that cooling that we've imposed in one basin to another part. And I think you can think of that as a general rule for something like marine cloud brightening. You see a lot in these early modeling studies where, you do brightening at one spot, you get some strong response of the opposite sign somewhere else, and you kind of get this patchwork of cooling and warming when you do marine cloud brightening. That's because you're imposing these really strong cooling effects in really concentrated areas versus something like stratospheric aerosol injection, which is kind of like a more blanketed diffuse cooling over a larger area. And then you see less of these intense responses of the opposite sign in other places. So that's kind of one of the main features of marine cloud brightening that's maybe different than other types of climate interventions.
Thank you. Mark has a question. I think you mentioned the possibility of MBC causing heat waves in certain developed regions like North America, Europe, China. If so, is this related to, for example, the reasons given by the work of Keyes et al. In their 2022 paper you may know called Potential for Perceived Failure of Stratospheric Aerosol Injection Deployment?
Yeah, that's a good question. I don't know if, it's really like based off of that work or if there's a direct connection between it based off, they're using stratospheric aerosol injection and we're using marine cloud brightening. I think it's maybe a feature of like we were just talking about these mid-latitude interventions. Yeah, I think this is really just one example, this study of a regional marine cloud brightening causing remote effects. I think you could do the same study, but move the patch where we're doing marine cloud brightening somewhere else, and we get totally different teleconnections. And I guess maybe the bigger takeaway from this work is not necessarily that, oh, if you do marine cloud brightening, you're going to cause heat waves in Europe and North America, but that if you do marine cloud brightening in one spot in the world, you might cause unintended side effects in very different parts of the world that were not intuitive, not, nearby where you were doing the brightening in the first place. And that's kind of the big takeaway, is this unintended side effect in any remote region, not really focusing on Europe in particular or North America in particular. So that's what I would say. Yeah.
Thank you. And those are all the questions that have come in through the chat. And I just wanted to ask you, I guess, what are one or two big questions that you have? Like, what's next for you? What are you trying to still find out? What are your next questions and pursuits in this area?
Yeah, thanks for that question too. I think that kind of feeds nicely off of what I just said. This is really a first stab at some of this regional marine cloud brightening work. And I think there are a lot of outstanding questions remaining in the field. And so, this study was looking at, could we do marine cloud brightening to benefit a particular region, just, close by. Some of my future work is looking at, how we can use regional marine cloud brightening to tap into things other than just, global warming, but potentially climate variability. So not altering the long-term mean state, but targeting particular events on shorter time scales, such as El Nino. That's kind of like the big one that people know about. Could you deploy marine cloud brightening at a time and location that would feed off of or inhibit El Nino events, something like that. And I think that could be another way that we think about deploying something like marine cloud brightening on a regional level, that maybe wouldn't have such far-reaching long-term effects, but could target, really hot events or something like that, that we could predict with ENSO forecasting. So that's kind of another question that I'm after currently, is using marine cloud brightening for not just changing the mean climate, but for climate variability purposes. Yeah, and I think this work is really just the start. I mean, there's so many different regions that this could be deployed. A lot of people are focused on the Arctic as well. And if we could do something like marine cloud brightening in the Arctic to just protect the Arctic from warming, I think a lot of the infrastructure is built with this groundwork that I just talked about, but there's a lot of ways that we could go next. Yeah.
Thank you.
Kathy, if I could add
yes,
please.
To
those points that Jessica's just made. One of the potential applications of marine cloud brightening is to reduce the intensity of hurricanes, so also cyclones and typhoons, because the category of a hurricane is in large part determined by the sea surface temperature. So if you target the sea surface temperature in the hurricane nursery zones, then instead of getting a category 5 that's incredibly destructive, it might cut back to a category 2. And with the intensity of hurricanes increasing, that's something that it's really a security issue and also an insurance issue, because lots of places are becoming uninsurable because of the frequency of hurricanes. And so if we could use marine cloud brightening to reduce hurricane intensity, especially, for example, in the central Atlantic, that would be a really valuable thing, and really the sooner the better, because we're seeing the worsening intensity, and it's like planting a tree. The best time to do it would have been 20 years ago, but the next best time is right now. And similarly with the Arctic, the impact of the melting of the Arctic on world weather is really chaotic and really quite dangerous. And so preventing the Arctic and Antarctica from melting is a really urgent priority, both for the the temperature, and also for sea level rise. We've got this risk of a couple of meters of sea level rise in this century, which again would be catastrophic. And so if we can cool down the poles, then that makes a really big difference. And it's not just doing MCB in the Arctic, but to cool down the currents of water that are flowing into the Arctic. So the mid-latitude MCB that Jessica was describing in the North Pacific would possibly also have a significant impact on the speed of melting in the Arctic.
Thank you. Thank you, Robert. We do have a couple other questions that have come in from Barbara. Since the International Maritime Organization imposed strict air pollution standards for the sea surface temperatures in the North Atlantic shipping lanes have dramatically increased. Could MBC be deployed to counteract this sudden ocean heating?
Yeah, I mean, I think it certainly could be. It would be hard to target, I think, just the specific areas where shipping emissions have been reduced, unless you're going to go out there and do them right where the ships were previously. But I'm sure it could be used in that application as well to kind of regenerate some of the cloud brightening that was lost by the shipping emissions. Potentially, there would be other better ways to do it than just marine cloud brightening, but I don't see why marine cloud brightening should be ruled out as a way that you could counteract that.
Thank you. From James, according to Professor Stephen Salter, as long as you can get the water droplets down to 0.8 nanometers in width, the majority of them would be raised up by the natural convection of the ocean temperatures. Do you have any insights about the technical challenges of producing water droplets of this size?
I do not have any technical expertise on that topic, so I think I'm going to have to not answer that question because I don't have any expertise to answer that with. But I think there are lots of folks in the world who are working on that question right now in both Australia, UW, and I think there's some folks at the Climate Repair Center in the UK. So yeah, lots of people probably have a better answer to that question than I do.
I'll just add a little bit on that if I could, Jessica. The issue is that the particle size needs to be really small, and so that's 0.8 microns is a really small salt particle, and making a nozzle that can generate such a small particle at an even spread really requires a lot of work. And so there are groups, for example, the Centre for Climate Repair at Cambridge University, and Ocean Cooling Technologies is the company that was established by Stephen Salter in Edinburgh at the Lothian School of Technology, and various others are also working on this technology of how to generate the submicron monodisperse salt aerosol spray. And it hasn't been proven that as yet that it's physically possible. So there needs to be a lot more investment into this question of how to do it. And then there's a bunch of other methods, like you could use silicon wafers, you could use electricity, you can use dry salt, make the particles, and then what happens to the particles when they're emitted. The idea is that if you create a nozzle using really filtered seawater, then once the particles are once the spray is emitted, then it dries off and forms an even spread of salt aerosol, and that forms a blanket over the ocean, and then that heats up with the sun and then rises up into the clouds. So the whole question of whether it's even possible, still hasn't been proved. And the Australian experiments on the Great Barrier Reef, they used particles that were bigger than the experts have suggested is optimal, because people still haven't been able to work out how best to do it. And also there's this question of how much electricity would it use? Like, finding a way to do it that's going to be cost effective is another really big challenge. So there needs to be a lot more research into the physical science basis alongside the modeling of climate impacts.
Thank you. Thanks for adding, Robert. Appreciate it. Jessica, we have a question from Herb. Is there a comprehensive NBC research agenda that has been developed and agreed to by the NBC research community? And should there be?
Yeah, there's been some work. Michael Diamond, who I think spoke on this series before, he had a paper out on research checkpoints for marine cloud brightening that came out, I think, a couple of years ago now. And it's kind of lays out, the checkpoints that we should consider, like all the way from particle generation to these large scale climate impacts, as well as exit ramps for when we should maybe not be doing this type of research anymore, or if we find some crazy finding that would suggest that maybe we should stop. And that's sort of, to my knowledge, the biggest research agenda that's in place now for marine cloud brightening research. But I wouldn't say it's agreed upon by any large community yet. They just kind of propose that as one way. The review paper I mentioned, Graham Feingold's paper that came out this year in Science Advances, that one also lays out kind of, the physical science research needs for marine cloud brightening that a group of experts determined is currently the main priorities right now. But again, people are just throwing this stuff out there. It's not agreed upon by any research community yet. It's just kind of what people see as the biggest challenges and pathways forward. The National Academies has a report on solar geoengineering as a whole for things that include stratospheric aerosol injection, cirrus cloud thinning, and marine cloud brightening, and kind of the research roadmap they perceive as, kind of where we're at and where we need to go. And they cover both the physical science and social science needs in that report. So there are lots of resources out there that kind of lay the groundwork for maybe what a internationally agreed upon research community should follow, but nobody is actually following it like to a T right now.
Thank you. So I think we're going to wrap up. We're about out of time, and we want to thank you so much, Jessica, for coming to MEERTALK today, for furthering our climate education, for helping us be aware that the effectiveness of marine cloud brightening can change as our climate changes and gets warmer. A lot to think about.
Yeah, thanks for having me.
Yeah, it's been our pleasure. Thank you so much. At MEER, we are working to help educate the public while also developing a solution to the warming on the planet. We invite you to keep learning about Earth's energy imbalance and climate science on our website. We're a mostly volunteer staff, so please consider making a monthly donation of any amount if you have enjoyed being here or watching our MEERTALKs on our YouTube channel. Also, please check us out on social media. If you have found being here today beneficial, please tell someone about MEERTALK. We hope to see you all again next month on Sunday, September 1st, when Vishwana Srikantaya will be our guest speaker. And until then, take good care, and thank you so much for coming.